Next we will obtain the second Ehrenfest equation starting with the second condition, which is V1 equals to V2. And we already have that during the second order phase transition the temperature and pressure are constant along with Gibbs free energy, entropy and volume. So this is here we are taking the second condition, V1 equals to V2. So suppose during some this second order phase transition happens at suppose temperature T and pressure P, then the specific volume V1 for phase 1 is equals to specific volume of phase 2 equals to V2. Now if the same transition happens at a different temperature T plus delta T and different pressure P plus delta T, then the specific volumes being function of temperature and pressure, their values will also change. Okay, let's say V is a function of temperature and pressure, so at a different temperature and pressure their values will be different. So for phase 1 the specific the value of specific volume is V1 plus dV1, and for phase 2 the value of specific volume is V2 plus dV2, and they are equal. This is the condition of second order phase transition. So in the next we will cancel V1 and V2 and we will have dV1 equals to dV2. Now as we have assumed that the specific volume is a function of temperature and pressure, what we have here dV, we can write dV in this following way. So from this dV1 equals to dV2, what we get, this relation del V1 pt dt plus del V1 del P constant T dP equals to, on the right hand side we have the phase 2 terms del V2 del Tp del V2 del P constant T dP, etc. Okay, now we have this isobaric volume expansivity, which is written as this 1 by V del V del T constant P. So here we also have similar kind of term del V1 del T del V2 del T, that is del V del T terms. So we can replace del V del T with alpha V, and then we have this del V del P term. We will replace this with this isothermal volume compressibility, which is beta T, because we know beta T is minus 1 by V del P constant T. So therefore del V del P constant T is minus V beta T. So if we replace with these terms, what we get on the left hand side, we have the V1 term, so it will be phase 1 term. So for we have isobaric volume expansivity for phase 1 alpha 1 V1 dt, minus we have again the phase 1 term, so it will be replaced like this with V beta T term. So for phase 1 terms V1 beta T1 dP equal to, on the right hand side we have only the phase 2 terms, so this del V2 del T will be replaced by phase 2 terms, that is alpha 2 V2, minus this del V del P terms will be replaced by the phase 2 terms, that is minus beta T2 V2 dP. In the next step what we are doing, we are writing this dP terms together and these dt terms together, and you also know that V1 equals to V2 equals to V, let's say. So what we can do, we can take we can replace V1 and V2 simply with V, and if we take common V, then we have beta, the dP term will be like this, beta T2 minus beta T1 V dP equal to, on the right hand side we have dt term. We have made V1 equals to V2 and we have written them as simple as V. We can take V common, so we have alpha 2 minus alpha 1. So finally what we have again the similar term dP dt, which is alpha 2 minus alpha 1 divided by beta T2 minus beta T1, and from this we got starting with V1 equals to V2, and then we have, this is the second Ehrenfest equation, and we had the first second Ehrenfest equation dP dt, which we got starting with this one equals to E2. So these two are Ehrenfest equation. So from the first order phase transition we started with G1 equals to G2, and we got dP dt to be the L by T V2 minus V1, which was the Clausius-Clapeyron equation. Here also we got the similar kind of term dP dt, that is the change of pressure with temperature for second order phase transition, and we get this Ehrenfest equations.